In this lesson, we're going to be taking a look at the deceptively simple looking yet very powerful and very important concept of function pipes. So, to set the stage, let us review the problem that we talked about in the last lesson. Namely, we took the Galapagos land snail data and asked the question how many distinct species there are in that dataset, and we also wanted to know their names. So, the solution we gave combined the select function with the distinct function. Here is the review of that solution. So first of all, we load the tidyverse. Of course, we're going to be using that. Then we load the dataset using readDlim and assign it to the variable snails. So far, so good. And the actual solution is in the final line. Namely, we first of all select the single column species from the snails dataset. So that is what select snails, species does. And what this does is it returns a table with a single column, which only has species in it. And then we apply distinct to that. And what distinct does is it removes duplicate rows. It deduplicates the data. So that means that since we had only one single column with the species names, those will be deduplicated, and we ended up with a table with only those species names that this dataset contains listed only once for each of them. Now, we mentioned that what this example does is it illustrates the composability of the different tidyverse functions. Namely, because each of the functions take the tibble that they work on as their first input and return yet another tibble as their output, they can be composed freely. And this is exactly what we do here. We chained together the functions select and distinct. First we applied select, then we applied distinct. Okay, that's all good and well, but what would it look like in a more complicated situation? So here is a slightly more complicated version of the exact same problem. Namely, here is the description. We want to display the species names in the data, but with the genus name also added. Remember, all these snails come from the genus Nasiotus, so we will want to add that to the names. And also we'll want to sort these species in alphabetical order. So as usual, there could be many possible solutions to this problem. But one very natural one breaks down the solution to the following steps. First of all, we will choose the species column only using the select function. Then we will deduplicate, just like we've done before, with the distinct function. So then we will end up with a table which only has one single column, namely species, and each species will be there only once. Then we can add Nasiotus to each of the names using the mutate function. And finally, after having done that, then we can sort all the rows in alphabetical order using the arrange function. Alright, so how can we actually implement this solution? One way to do that is by using repeated assignments to variables, although as we'll see this is not necessarily the best solution, but it definitely works. As you see, it looks a little bit messy, so let's break it down line by line. So first of all, we define a new variable called snail species, which is equal to then select snails, species, which means we just choose that one single column from the snails dataset, namely the column species. So in other words, the variable snail species will contain a tibble with a single column, which will be species. In the next line, we deduplicate. So snail unique is another variable to which we assign distinct of snail species. And snail species is a result of the previous line, namely, it is the table with the single column. So now we deduplicate those entries. So snail unique will end up with a table which has a single column and only as many entries as many species. So that is, in a way, the solution to our original simpler problem. Moving on with the solution, next we define snail names full, which will simply attach the genus name Nasiotus to each of the species. How is it being done? Well, the way it is done is we apply mutate to the table snail unique. And when we redefine the column species in the following way, we apply paste of the character string Nasiotus and species. If you recall from quite a few lessons ago, the paste function takes two character strings and puts them together into a single string, interspersed by with a space character in between them. So that will be good. That takes care of the space in between the genus name and the species name. And what happens here is the first part of paste, the first argument of paste, is Nasiotus as a character string. That's why we have the quotes around it. And the second argument to paste is the species columns entries. Again, whenever we refer to a column by its name in one of these tidyverse functions like mutate, we mean the vector of entries. So what this will do is it will take the character string Nasiotus, it will take the vector of strings species, and to each of those it will attach the character string Nasiotus at the beginning. Alright, so after that, the final step to be done is simply to arrange the names in alphabetical order. We do that with the arrange function. So we take snail names full, the result of the previous line, and arrange it based on the species column and assign the result to the variable snail names sorted. And if we want to print what snail names sorted looks like, here is the result, and it is exactly what we wanted. This table has a single column and 7 rows. Each row corresponds to a single species. Each of the species names is prepended by the genus name, Nasiotus, and the rows are in alphabetical order, beginning with Calvus, ending with Ustulatus. Alright, so while this solution definitely works, there are several reasons to think that maybe it is not the best that one can do. So why is that? Let's see. First of all, as you can see, we have to invent a new variable name at every step along the analysis process. And that get a bit unpleasant, especially because we're unlikely to use these intermediate variables again. So for example, snail unique, which we defined just to be able to compute the next step, is unlikely to be used anywhere else except in that next step where we compute snail names full, which incidentally is also not going to be used ever again except in the next step. So it's a bit wasteful, and it forces us to invent these names. One solution could be, you might think, is, well, why are we inventing these names? We should just use the snail's name, the original name for the original data, and keep overwriting it. We could do that, however, earlier in the course I already warned about the dangers of overwriting variables. I also made the promise that I would try to teach you a style of programming that relies on overwriting variables as little as possible. So I will keep true to that promise. So while of course one could do that, and instead of inventing the names snail species and snail unique and so on, just overwrite the snails variable at every step, we're not going to be doing that either. Incidentally, there's one more disadvantage to doing things in this way, namely, it is a bit of a nuisance to modify things around. So imagine, for example, that we want to insert yet another step in the middle of this pipeline. In that case, first of all, we would have to invent yet another name. But more than that, we would have to use that new name in the next step in the analysis, which means we would have to go down and modify more code. And if we just forget to do that, then of course nothing will work. So it is easy to make mistakes if we program in this style. So all in all, we're trying to move away from doing things in this manner. So if we're not going to be relying on repeated assignments, then how are we going to solve this problem? Well, in fact, we can work in analogy with the simpler problem that we've had earlier. And remember, the solution was to chain functions together, that is, apply different functions to the results of the previous function applications. So in this case, we first select the species column from the snail's dataset and then deduplicate its entries by using the distinct function. So following that same schemata, we can then write our solution to the more complicated problem like this, where we do the same thing as we did earlier. We select the species column from snails, deduplicate, then we mutate the Nasiotus genus name onto the species name on that, and then we arrange by species. Whoa, what's going on here? Well, let's take a more careful look maybe to dissect this. So at the top I have the exact same thing that you've seen on the previous slide, the messy solution. And let me try to break it up into lines at the bottom block just so that I can tell you a little bit more easily what's going on. Notice that there are line numbers there on the left margin. Those are just for indication. Those are not part of the code. That's for me to make it easier to talk about the code. So let's see what we're doing here. It all begins on line 4. Select snails, comma, species. That's sort of the center of this messy expression. Then, after having selected that column, we apply the distinct function. So far so good, nothing strange. And then we apply the mutate function in lines 2 to 7 to that result. And namely, we take the table that is returned by the distinct function and then mutate the species column by pasting it together with the genus name Nasiotus. And finally, we take all of that and make it the argument of the arrange function. So now we're through lines 1 to 9 and then arrange all of that by species. So that is what was written a bit more compactly in the top block, but otherwise the two are completely equivalent. They're just arranged a little differently. Okay, so you might justifiably think at this point that while we've successfully avoided the problem of having to invent new variable names all the time with this solution, but we might as well go back to that because this is so horrible, so unreadable, so unmanageable that it was better to do that kind of solution. And if that's what you're thinking, I can definitely empathize with that. This is the point where function pipes come into play. And to understand the basic concept, let us take a very familiar example. We take the square root of a number, simple function application. So we apply the function square root to the number 9, we get back 3, everything is fine. As it turns out, there is an alternative notation for the same thing. Instead of writing down the name of the function and then the argument in parentheses, we can write the same thing in this manner. The vertical bar and the greater than symbol together, they are written next to each other, they form a single operator and that is called the pipe. And the way we read this is that we feed in the number 9 into the function square root. So the pipe reverses the order of the name of the function and the argument that the function is applied to. So instead of writing down function, the name of the function, and then what argument we apply that function to, we first write down the argument, then the pipe symbol, and then the function that we're going to be using. So this notation can be used with any function whatsoever, and here's a little table summarizing how the pipe actually works with an arbitrary function f. So in the top row, you see what happens if the function has just a single input, a single argument called x. In that case, we do exactly what we've done above. Instead of f parentheses x, we're allowed to write x pipe f. Everything's good. But we can also use the pipe operator with functions that take multiple arguments, and in that case, the pipe will automatically apply to the first argument of the function. In other words, if we have a function f and it has multiple arguments, x, y, and so on, then we can write that same thing equivalently as x pipe f of y and so on, omitting the x from after f because that is the variable that we're piping in, so that will automatically get substituted in as the first argument to the function f. So what you see is that the form on the left is always completely equivalent to the form on the right in this table. Okay, let's see a couple of simple examples of how this might work. If we want to compute the cosine of the logarithm of the square root of 256, we can write that in the traditional way, but maybe for a human brain, it is a bit more transparent to write it the other way. We take the number 256, then we take its square root, we pipe it into the square root function, then we pipe the result of all of that into the logarithm function, and finally we pipe the result of all of that into the cosine function. So the equivalent piped form moves along in steps that we tend to think of. First we take a number, then we do this operation, then we do the next operation, and finally we end with the final operation. So that can really be closer to how humans think than machines think, even though the two forms are actually, to the computer, completely equivalent. Let's consider a small variant of this same example. As you can see, it's almost exactly the same expression, except there is this extra base equals 16 argument somewhere there. And I say the word somewhere because if you just look at that line casually, it's not that transparent to see which function that actually belongs to, which is one of the main disadvantages of using the traditional notation for functions. This is one of the places where pipes can really help out. So let's see how we can rewrite this same expression with pipes. We start with the number 256, then we apply the square root function. We feed the number 256 into square root. Then we feed that into the logarithm function. And now it's clear that the base equals 16 is part of the log function. Again, we didn't write out which number we take the log of because that is implied to be the thing that we pipe in. So we don't even need to specify that. And then finally, we pipe all of that into the cosine function. As another example, let us take a look at the simpler problem that we began with today, namely how many snail species there are in the land snail dataset and what their names are, but without attaching the genus names and sorting them alphabetically. So we know the solution was to first select the species column from the snails dataset and then deduplicate the rows using the distinct function. We can rewrite this in the way that you can see on the slide, by starting with the snails dataset, piping that into selecting species, and then finally piping that into distinct. And notice that something very convenient has happened here. We no longer need to specify as the first argument to these functions the table that we worked with. Why not? Because that is exactly what the pipe does automatically. So again, remember, the pipe silently substitutes in as the first argument of a function whatever is to the left of the pipe. So if we have snails, pipe, select species, that translates literally to select snails, comma, species. And then we repeat that when we go on to the distinct function. Alright, so with that we are finally ready to actually solve the original problem that we had in a way that is transparent and simple and also does not rely on unsafe things like redefining variables. We can do that by taking the original ugly solution that we didn't like and rewriting it using pipes. And when we do that, what we do is we start with the snails dataset, and then we pipe that into the select function, so we select only the species column from that. The output of that will of course just be the table with only that single column, and we pipe that into the distinct function. Then we redefine the species column by putting the word Nasiotus in front of every species name, and finally we pipe that into the arrange function to arrange the rows in alphabetical order. So please do notice just how delightfully simple and transparent this program became, especially if you compare it to that mess that's at the top of the slide, which is completely equivalent to the piped form. It's just that a human has a hard time reading the first version and a much easier time reading the piped version. So the piped version really reads like a sequence of instructions, right? We start with the snail dataset, then we select, then we deduplicate, then we mutate, then we arrange. And that makes it easy to think about, that makes it easy to insert new steps in the workflow if we need to without any problems. So this is really the big advantage of using pipes. And the reason it works so nicely, if you think about it, that these functions that we've been talking about from the dplyr package, like select and distinct and mutate and arrange, all of these work in the same way in that they take a tibble as their first input and produce yet another tibble as their output, which means that they can be very straightforwardly chained together with a pipe. Because, right, when they receive an input, that's always the tibble that's going to be their first input, and they themselves produce a tibble as their output, which then can be used as the input for the next step in the workflow. One more small comment. You see that in this program we start with the snails dataset, but if you remember from the very beginning of the lesson, the snails variable was defined as the table that we read in from a file. But that means that we might as well not bother assigning the variable, and if we want to, we can rewrite this program by changing its first line to the readDelim function. You don't have to do this, but you can do it this way, and then you don't even need to bother assigning that variable. All you do is first you read in the contents of the file, which returns a tibble, then you feed that into the select function, and so on and so forth for the exact same steps that we have been doing. And again, the output from this workflow is exactly what we wanted and what we've seen before, so it's all the species, only once, with the genus name and in alphabetical order. So that's pretty much it for today. This is how the pipe works, and from now on in this series of lessons we will be heavily relying on the pipe operator, so please be sure to be comfortable with the piping notation. There is just one small technical remark I still wanted to make, namely to be able to use the pipe operator you do need to have R 4.1 or later installed on your computer. So my recommendation would be that if you need to, you should upgrade your R version. That's the simplest solution to be able to use the pipe. But if for whatever reason that is not an option for you, then let me tell you about a simple workaround. Namely, the tidyverse also has its own version of the pipe. So if you have the tidyverse loaded, which you should because we're going to be using it every time anyway, then instead of writing this vertical bar greater than symbol, you can write the % greater % symbol, which is the tidyverse version of the pipe. And for the purposes of this course, it works exactly the same way as the pipe that we've been learning about. Yes, there are other features and other more complicated use cases where their uses slightly differ. If you're, for example, taking the more advanced course on data analysis at Linköping University, we will be talking about that when we get there. But for the use cases that we're going to be talking about in this course, they work in exactly the same way. So you don't need to do anything except replace the pipes with this % greater % symbol. So that's it for today. Thank you for your attention, and I will see you next time.